If you read a sentence like, "The man went to the blank store," you can effortlessly fill in the blank. You do this by looking at the words that come before the blank and the words that come after. Up until late 2018, language models struggled to do this. Standard conditional language models process text sequentially, predicting the next token based exclusively on what had already been read. This forced architectures into one of two patterns. They either ran strictly left to right, like GPT, or they processed the text forward, processed it backward, and glued the two separate outputs together at the very top, like ELMO. That shallow connection is a structural liability. For understanding tasks like question answering or natural language inference, the meaning of a word hinges on the context that surrounds it on both sides simultaneously. A strictly sequential read strips the model of that context. To mirror how humans read, we need deep bidirectionality, giving every token the ability to look at its left and right neighbors in every single layer of the network. But if you attempt this with a standard language model, you hit a paradox. If a model is allowed to look in both directions through multiple layers, the target word eventually indirectly sees itself in the input. The model bypasses learning semantics, simply spotting the target word in its context window and copying it. In 2019, Google AI Language published BERT. To solve the copy paradox, they did not invent a complex new architecture. They recognized that the training objective was fighting the architecture, so they changed the objective. To understand how BERT changes the rules of language modeling, we have to look at the data flowing into it. The model pre-trains on a massive corpus, 3.3 billion words sourced from the books corpus and the entirety of English Wikipedia, processed at the document level to preserve contiguous context. Two raw sentences from this corpus are packed into a single sequence. Every sequence starts with a special classification token, CLS. Then comes sentence A, a separation token, SEP, sentence B, and a final separation token. This raw text is broken down into a 30,000 token wordpiece vocabulary. Each token is converted into a numerical token embedding. Because the model needs to know which sentence is which, a learned segment embedding is added to mark tokens as belonging to A or B. Finally, a learned position embedding tracks where each token sits in the sequence. Rather than concatenating these three arrays, which would bloat the memory footprint, the token, segment, and position embeddings are simply summed together element-wise. The resulting array maintains a strictly controlled hidden dimension size. By packing identity, sentence structure, and physical position into a single vector, this shared input architecture is equipped to handle long document pairs during pre-training and specific single-sentence tasks later on. The backbone processing these unified embeddings is the standard Vaswani transformer encoder. It relies on multi-head self-attention and feed-forward networks, utilizing a GELU activation function. BERT achieves deep bidirectionality strictly through subtraction. It takes the standard transformer block and deletes the causal triangular mask, the specific piece of code that blinds a model to future tokens. Google released two versions of this unmasked architecture. BERT Base operates with 110 million parameters across 12 layers, explicitly matched to OpenAI's GPT for direct comparison. BERT Large scales up to 340 million parameters across 24 layers. This unmasked architecture sees the entire sequence at once. It is highly optimized for understanding, but because of the copy paradox, it is entirely untrainable using standard prediction tasks. The mechanism that makes this architecture trainable is the masked language model, or close task. The system randomly selects 15% of the input word pieces for prediction. The order of operations here is rigid. Before anything is altered, the original identity of the selected token is captured and saved as the target label. Once the true label is safely stored, the chosen token in the input sequence is replaced with a blank mask symbol. This mutation must happen in the input text itself. If the token was merely hidden within the attention layers but left intact in the input, the network would eventually route around the blind spot and copy the data. The mutated sequence runs through the encoder. The model attempts to predict the missing word based on the surrounding text, and cross-entropy loss is computed exclusively on those 15% masked positions. By physically removing the target from the input, the identity shortcut is severed. The model is forced to infer the missing word from its left and right context, making the deep bidirectionality of the architecture finally trainable. Masking solves the copy paradox, but it introduces a structural flaw. The mask symbol is entirely synthetic. It exists during pre-training, but it never appears when the model is applied to real-world tasks later. To prevent the network from over-optimizing its internal representations for a symbol it will never see again, BERT applies an 80-10-10 replacement rule to the selected tokens. Of the 15% chosen for prediction, 80% are replaced with the mask symbol, 10% are replaced with a completely random real word from the vocabulary, and the final 10% are left as the unchanged original token. This is computed via a single uniform random draw evaluated against fixed thresholds. It is one roll of the dice per position, ensuring the outcomes are mutually exclusive. Because the model never knows if a token is masked, random, or correct, it cannot rely on the mask symbol as a crutch. It is forced to maintain a robust, mathematically useful representation of every single token, a feature that protects performance when the model is used as a frozen feature extractor downstream. While the masked language model trains the network to understand individual words within a sequence, it does not teach the model how two separate sentences relate to one another. To build this capability, BERT employs a second pre-training objective, next sentence prediction. Half the time, sentence B is the actual logical continuation of sentence A. The other half, it is a completely random sentence pulled from the corpus. The model reads this binary prediction, is next or not next, directly off the final hidden state of that special class token placed at the beginning of the sequence. Because the attention mechanism is deeply bidirectional, the network doesn't need a complex pooling layer here. The .cls position automatically aggregates information from the entire sequence pair in every layer. The final pre-training loss is simply the sum of the mean masked likelihood and the mean next sentence likelihood. Executing those calculations across a 3.3 billion word corpus requires immense hardware. Pre-training BERT large for 1 million steps at 128,000 tokens a batch required 64 TPU chips running continuously for 4 days. While that pre-training requirement is massive, that cost is incurred exactly once. After pre-training, fine-tuning the model for a specific commercial application takes roughly an hour on a single TPU. This relies on unified fine-tuning. You initialize the heavy pre-trained encoder and add a single lightweight output head specific to your task. For question answering, this head is remarkably thin. The model learns just 2 parameter vectors, a start vector and an end vector, which are dot producted against the paragraph states to locate the specific span of text containing the answer. You fine-tune all the parameters together, but the heavy lifting of language comprehension is already done. BERT shifted the economics of the field by allowing dozens of applications to reuse one pre-trained understanding phase. When BERT was published, it set new records across 11 natural language processing tasks. But how do we know the masked language model objective drove those results, and not the sheer scale of a 110 million parameter architecture? The proof is Table 5. Researchers conducted a controlled ablation study, holding model size and training data perfectly constant. The only variable altered was the training objective. When forced to predict left to right, token-level performance collapsed. The squad question answering score plummeted from 88.5 to 77.8. Meanwhile, tasks that analyze a single sentence as a whole, like SST2 sentiment analysis, barely moved. And when they removed the next sentence prediction objective, accuracy primarily dropped on sentence pair tasks like QNLI, validating the need for the second objective. The left-to-right failure is isolated specifically to tasks requiring deep contextual understanding. This ablation data isolates the variable. Adding parameters does not guarantee comprehension. Deep bidirectionality is the critical mechanical lever for natural language understanding, and the masked LM objective provided the specific mechanism that made it possible.